Good morning, everyone. Welcome to today's webinar on Janmabhoomi Temple at Ayodhya, Geotechnical Investigation and Foundation System. My name is Pooja Dobhal. I am the Marketing Coordinator at Cengrs and your moderator for today's webinar. The Ram Janmabhoomi Temple in Ayodhya stands as one of the most iconic and historical significant projects, embodying the spiritual and cultural aspirations of millions. As we mark the one-year anniversary of the temple's grand inauguration, we reflect on its engineering marvels and deep-rooted heritage. It's an honor to introduce our esteemed speaker for today's, Mr. Ravi Sundaram, Director of Cengrs Geotechnical. With over 44 years of experience in the geotechnical engineering industry, Mr. Sundaram has significantly contributed to the field, particularly in geotechnical investigation, geophysical survey, ground improvement, and groundwater studies. He has published more than 70 technical papers, each reflecting his vast expertise and practical experience in geotechnical engineering. Among his many accolades, Mr. Sundaram has received the prestigious IGS Professor Dinesh Mohan Memorial Award for Excellence in Professional Practice and the IGS Delhi Chapter Lifetime Achievement Award in 2012. In 2017, he delivered the prestigious 6th Madhav Lecture, an honor bestowed in memory of Professor Madhav, former Vice President Asia ISSMG. Furthermore, he is an active member of several committees under the Bureau of Indian Standards and Indian Roads Congress. We are indeed privileged to have such an accomplished expert with us today to discuss the geotechnical challenges and innovations behind the foundation system of the Janmabhoomi Temple at Ayodhya, a project of immense cultural and structural significance. Before we begin, I encourage everyone to participate actively. Feel free to drop your questions and comments in the chat box, and we'll address them live during the Q&A session. Over to you, sir.
Thank you, Pooja. Welcome to this webinar on Shri Ram Janmabhoomi Temple at Ayodhya. We will be talking about geotechnical investigations and foundation system here. This event commemorates 1 year of the inauguration of the temple at Ayodhya, which was done on January 22nd last year. So it has been a monumental structure. A very huge team of various experts had participated and contributed to the development of this mammoth structure. And this is the time to thank every one of them, acknowledge their contributions, and move forward. So right at the beginning, I would like to acknowledge the contribution of various experts. The owner, the client, was Shri Ram Janmabhoomi 𝗃𝗃 Trust, which was formed for building the temple. An 8-member expert committee chaired by Professor V.S. Raju, a very eminent and recognized geotechnical engineer, former director of IIT Delhi. He chaired this committee. There were several other experts. One person to which I am very grateful and thankful is Professor 𝗔𝘆ecie Sitaram. He was formerly the director of IIT Guwahati, and currently he is the chairman of AICTE. I'd also like to mention about the temple architect, C.B. Sompura. He comes from a lineage of very eminent family which had done the design of the Somnath temple over 2000 years ago in Gujarat, Dwaraka. There were others, the Argon engineers, structural consultant, Tata Consulting engineers, and the PMC. Also, it was Larsen and Toubro Limited, the contractor, who actually built the temple. So what you see today is the efforts of L&T. There were various others experts who contributed. There was the NGRI Hyderabad, CBRI Roorkee, IIT Madras, and the geotechnical investigation was done by Cengrs Geotechnical, and that is how it all started off. So all the stakeholders, the experts, and others involved in the project, I gratefully acknowledge their contributions. So just a brief introduction on what this presentation will include. The history, the legal cases, and the temple as planned and architectural principles which were involved here. The geotechnical investigations and geophysical investigations. That's the main thrust of this presentation. I'll be talking primarily about this. There will also, so it will contain the test results, what were the tests done and what were the results, the geotechnical design profile, the liquefaction analysis, the expected behavior of the temple during earthquakes, various foundation alternatives which were evaluated, and what was the final foundation system selected, and why we opted for this kind of a foundation system. So we'll talk about the excavation, the engineered fill, the quality assurance, and how the structure was assembled. I will also, towards the end, speak a little bit about the archaeological findings, and then we conclude. So brief history of the project site, the Ram Janmabhoomi Babri Masjid site. The site of the Ram Janmabhoomi land, the associated court cases, and the final selection of the site for the Shri Ram temple. This is a complex and deeply intertwined narrative of religion, politics, culture, and the Indian law. So when you talk about the engineering of the temple, we have to take into mind what had actually gone behind this, which is the non-technical aspects like the politics, the religion, the law, and all that. So obviously, as you are all aware, Ram Janmabhoomi is believed to be the birthplace of Lord Ram, seventh avatar of Vishnu, in the city of Ayodhya. The city has therefore been of religious significance to Hindus for centuries. In 1528, the Mughal general 𝗏𝗵𝗿, under the orders of Emperor Babur, is said to have constructed the Babri Masjid on this site. This is also mentioned in Babur's memoirs, Baburnama. The construction was completed in 1539, according to an inscription at the site. So it started in 1528 and was completed in 1539. Now, this has been a point of contention. Some believe that the mosque was constructed after demolishing a pre-existing temple. But of course, Baburnama does not mention this. The first recorded legal dispute over the site occurred in 1853, when a Hindu sect claimed a right to build a temple on the site. The British colonial administration divided the site in 1859, allowing Muslims to use the inner courtyard and the Hindus to use the outer courtyard. Now, the court cases and the developments that took place, 1949-50, idols of Lord Ram were placed inside the mosque, leading to both Hindu and Muslim protests. Government declared the site as disputed, and locked the gates, allowing worship only from outside. In 1950, Gopal Singh Visharad filed a suit seeking rights to worship the idols. Then there was this Mahant Paramahamsa Ramachandra Das. He filed another suit for continuation of puja and for removal of the idols. In 1986, the whole thing was split open with the reopening of the gates. District Court of Faisalabad ordered the gates of Babri Masjid to be open, allowing Hindus to worship the idols inside. The decisions reignited the dispute, led to the formation of the Babri Masjid Action Committee. In 1989, the Vishwa Hindu Parishad activities also increased and the legal battles intensified. So this led to a nationwide movement to build temple at this site. Another suit was filed on behalf of Lord Ram, basically Ram Virajman, by a VHP-backed organization seeking title to the disputed land. In 1992, on December 6th, a large crowd of activists collected there. A big rally took place by VHP and BJP. They demolished the Babri Masjid. This led to a widespread communal riots across India, resulting in deaths of thousands of people. Post-demolition, there were legal proceedings, numerous cases, including criminal charges against political leaders and activists. Sites remained disputed, and the courts took control of the land. Archaeological Survey of India was appointed to conduct excavations and determine historical facts. So 2002 to 2010, ASI did a lot of work. What they found was the evidence of a temple-like structure beneath the mosque. On September 30th, 2010, Allahabad High Court delivered a landmark judgment dividing the 2.77-acre disputed land into three parts. So 1/3 goes to Ram Lalla for construction of the temple, 1/3 goes to the Sunni Waqf Board, and 1/3 to the Nirmohi Akhada. All the parties contested the verdict. So then the matter goes to Supreme Court, and you are all aware that in 2019, November 19th, Supreme Court of India delivered its final judgment in the matter. The court unanimously awarded the entire disputed land to the deity Ram Lalla, represented by the Hindu parties, for construction of the temple. The court also directed the government to provide an alternative 5-acre land to the Sunni Waqf Board for construction of the mosque. So with this, all the disputes were over and the activities related to the construction of the Shri Ram Temple started. So the Shri Ram Janmabhoomi Tirtha Trust, this was established to oversee the construction of the temple. The foundation stone for the temple was laid on August 5th by the Prime Minister and then inaugurated again by the Prime Minister on January 2nd, 2024, that is last year. So now we go to what was planned. Now with all the history and the court cases behind us, I'd like to explain what was planned, how it was executed, the engineering behind the structure, how it got constructed, and what we see today. So this is the temple as planned. This was the architect's visualization of how it should look like. So the temple is basically planned as a masonry load-bearing structure. It is planned to last for nearly 1,000 years. The temple architect required that the steel shall not be used in the construction, as per the ancient Vastu and Shilpa Shastras of temple construction. Some religious scriptures also advise that temple structures be constructed without using steel for various practical reasons. Hindu temple architecture, based on ancient texts, designed the various principles of design, layout, measurement, ground preparation, and spatial geometry. So the design is rooted in the classical principles of Indian architecture, drawing from Nagara style. That is the style which is prominent in most of North India. So the key architectural features of the Nagara plan, Nagara style, include, it has a shikhar, a towering shikhar, or it is also called the Vimana. There is the Garbhagriha, the various mandaps. As per Vastu Shastra principles, it is made. The stone and materials usage here, sandstone, pink sandstone, Bansi Paharpur sandstone, that was used. Pristine white marble was used in most of the areas, and the granite plinth. So these are all important features here. The sculptural art, the iconography, cultural and religious aspects of the whole thing, all is rooted in the traditional Hindu architecture. Of course, there has been environmental integration, landscaping, and the sustainability aspects have also been looked into. As you know, it's a grand structure, but care has been taken to ensure public accessibility for large crowds. So this is how it looks like. There is the shikhar, 161 feet high, the Garbhagriha, and then the Gud Mandap, Nritya Mandap, and the Rang Mandap. The platform here, you would have to climb a few steps to get in there. So this is the front elevation, how it looks like. So let's look at Ayodhya, situated on the banks of the river Sarayu, which is also called Ghagra River. It is the headquarters of Ayodhya district. Earlier it was part of the Faisalabad district. Now it has been split into two districts, with Ayodhya being made a new district. So that is where the temple is located in Ayodhya. So it is about 1 kilometer northeast of the Sarayu River, and also 1 kilometer northwest of Ayodhya railway station. As you can see here, the temple site is on the highest point in the area. So let's look at this temple details. Plot covering nearly 67.7 acres. Of course, the main temple is built over 2.77 acres. The built dimensions are 115.8 meters by 76.2 meters. That is 380 by 250 feet. So the development here includes the Garbhagriha, which is the most sacred part of the temple, which has the statue of Ram Lalla. The highest dome is 161 feet. There is the Gud Mandap, which is a prayer hall. There is a Rang Mandap, which is a large sequential space in front of the deity. Then there is the Nritya Mandap. Which is a dance hall. Then there is a Pradakshina, a Chowki, of course the gate, the compound wall, or the Parkota. So this is the how the temple will look like as it was planned using the stone masonry concept. The stone structure was assembled by meticulously placing the precisely carved stones, each with grooves cut in them, which interlock into the next stone, essentially creating a puzzle like fit without the need for cement or mortar. Mm. So this is the traditional method, centuries old method to ensure durability while adhering to the traditional Nagara style of architecture. No iron or steel was used in the construction. About 20,700 large blocks of granite, 32,800 blocks of sandstone, and 7,200 blocks of marble have been used in the construction. So you can see here on the ground floor you have the main statue. On the first floor there is a Ram Darbar, and then there is a second floor. So this is how the structure looks like. So for protection against ground moisture, a 21 feet high plinth was constructed with granite. The foundation is flexible. It can accommodate some movement during earthquakes. The roofs and pillars are stacked in such a way that their center of gravities are perfectly aligned. So it's basically the enormous weight of the structure which holds it in place. Traditional construction methods, materials, and age-old building practices have been used. But of course, modern technology has been used for the construction activity. Steel has not been used for construction. Stone has a longer lifespan and better durability in comparison to reinforced concrete. That is why concrete was not used. Also, stone shall enhance the structure's earthquake resistance. Now we go into the geology and geomorphology of the area. So this is the temple relative to the Saryu River, the Indo-Gangetic alluvium. It's the whole area is a part of the Indo-Gangetic alluvium. As you know, the Saryu goes and joins the Ganga. So it is located in the floodplains of the Saryu River. So basically, Faizabad district, Ayodhya district are all part of the central Gangetic plains. So a thick pile of alluvial deposits of quaternary age, that is maybe between 1 million years and 10 to 15,000 years. This is the period during which the deposition took place. So the alluvium consists of unconsolidated sediments of clay, silt, conker, and sand. So they are all recent deposits, less than 1 million years old. The Saryu River has a large floodplain with several mid-channel bars. The channels are meandering. Multiple scars are present within the floodplain. So the temple, of course, is located here. This is the highest point. Adjacent to the temple, there's a cut-off bank. There's an abandoned meander of the Saryu River. There's a natural depression, or a paleo channel as it is called, near the temple site. Now, I go briefly into the geophysical investigations. Will not take too much time on the geophysical. We'll go more into the geotechnical aspects. So, geophysical investigations conducted include ground penetrating radar, electrical resistivity tomography, MASW tests, and micro tremor study. NGRI had done most of these studies. CBRI had also done some studies. So this thing, the ground penetrating radar identified a buried wall right at the location of the 𝗏𝗃. Then these are all these various soil depositions in the temple zone. So you can see here that this top layer is where there were a lot of artifacts found. Similarly, this is the electrical resistivity tomography. All these different colors which you see here, these are locations where they did find a lot of some of the artifacts. The MASW study, basically this found the top layer of dumped material with man-made islands, man-made materials. There was a water saturated zone here, and then there was the sands of different compaction levels. So the shear wave velocities measured here, these were used to determine the kind of how hard the soils are, and also a paleo channel was identified. So all this is mostly courtesy NGRI Hyderabad. So now I move on to the geotechnical investigation. As some of you may be aware, the purpose of the investigation is to identify the stratigraphy or the soil conditions to substantial depth below the ground, particularly the 𝗏𝗃, the various mandaps and other structures. Get a resistance of assessment of the soil resistance using a standard penetration test, determine the engineering properties of the soil, perform the soil bearing capacity and settlement analysis, evaluate the potential for liquefaction during earthquakes, and provide the engineering data for assessing the various possible foundation schemes so that you can select the appropriate one. So the locations of the investigation is selected dependent on the structural loading. So 𝗏𝗃 is the tallest dome, the heaviest loads. So maximum investigation was done there. And similarly, for the various mandaps, depending on the loading, the scope was decided. So that's a plan of the investigation. I'll go more into this. The investigation was basically in two parts. The first phase was the main temple and the boundary wall. For the main temple at the 𝗏𝗃, one borehole was done to 60-meter depth. 6 boreholes were done to 30-meter depth, and for the various mandaps and the temple platform. And then along the boundary wall, boreholes were drilled to 20-meter depth. The second phase was taken up after the excavation to about 3 to 5 meter depth was started. And once the excavation was done to around 5 meter depth in most of the area, this scope included one borehole to 120 meter depth, because we wanted to have an idea of how thick the soil layers are, and whether any rock is encountered at deeper depths. Also, pressure meter tests were done. These are advanced testing method to assess the soil behavior. 2 boreholes to 60-meter depth was done for the temple platform for some of these mandaps. And then 4 boreholes 40 to 50-meter depth was done for the small temples along the compound wall, because those are they are also heavily loaded facilities. Static cone penetration tests, these are also advanced tests. So 2 were done in the 𝗏𝗃 for additional data for foundation analysis. So as I told you, this is the plan of the investigation of the various tests. Here we are sticking only to the main temple. So this is the 𝗏𝗃. You can see this is the first 2 boreholes which were done initially, and then the second borehole, this third borehole, NBH1, this was started from after excavation. to 5-meter depth. So this borehole went down to 120 meters, as you can see. So I have data up to 60 meters here, and then it continues down here. So probably you should extend it here to 120 meters. So Ayodhya, as I told you earlier, is in the Indo-Gangetic alluvium. Now the superficial fill extends to 7 to 8 meter depth. Then below that you have sand, silty sand with minor layers of sandy silt. The fill contains basically silty sand with stones, brickbats, and all that. And at deeper depths, a few small pieces of pottery were also encountered. Below 50 to 55 meter depth, it is very dense, compact, silty sand to 120 meter depth. So we did not encounter rock to 120 meter depth. In fact, there was a 8 meter thick sandy silt plastic zone, low plastic material at about 84 meter depth. The sand below 94 meter depth exhibits some weak cementation. Groundwater was met around 15.1 to 15.7 meter depth. So you can see the groundwater level here. Now, this is the Gud-Mandap, Rang-Mandap, and the Nritya-Mandap. So here also we had boreholes down to maximum 60 meter depth. Stratigraphy is similar. The fill thickness is ranging from 7.5 to 15 meters. So you can see here the fill thickness was more. Again, groundwater 15.1 to 15.7 meter depth. So this is the pressure meter test being done at Ayodhya. So the pressure meter gives you pressure versus volume change. So this is the limit pressure and the deformation modulus profile with depth. And you can see the horizontal stress with depth. These are results of the static cone penetration tests. So this was done from the excavated level here. This is at the Garbhagriha. So this the cone resistance gives you an indication of how compact the soil is. So basically the test was done to about 40 meter depth. There was the fill and then the sand, as was interpreted from this friction ratio and the cone tip resistance. The Garbhagriha, again, now we can interpret various engineering properties from the cone penetration tests. So we had used the Robertson's correlations to assess the SPT values, bulk density, and various other parameters. So you can see what these show you the measured values of the densities in the boreholes, and then these are the interpreted from the cone penetration data, and this one is the design profile which has been used for our analysis. Same way, the density of the soil, these symbols here show what was measured in the boreholes, and we have the cone data, the interpreted density values, and the design profile. Also, we measured the angle of internal friction and the relative density interpreted from the cone data. So this is the same kind of correlations for the Gud-Mandap. Here also we had done the cone penetration tests, and you can see here there was the 6 meter fill and then the sand below, and below around 38 meters there was the silt layer. So this is the design profile of QC, cone tip resistance. various engineering parameters from Robertson's correlations, the SPT values, the bulk density, the friction angle, and the relative density. Modulus of elasticity is another very important parameter and little difficult to assess. The best correlations are available from CPT and pressure meter. So looking at all these, design profile for the modulus of elasticity has been selected for the 𝗏𝗃 and for the 𝗏𝗏 𝗏𝗏 area. So using all this, the geotechnical design profile has been selected. So this is the geotechnical design profile for the 𝗏𝗃. This is the geotechnical design profile for the 𝗏𝗏 and 𝗏𝗃 and the 𝗏𝗏 also. You can see the various parameters which have been selected for the foundation analysis. Seismicity and liquefaction analysis was performed. So first, a seismotectonic map of Ayodhya and its surroundings. This was prepared by CBRI Roorkee for determining the deterministic hazard analysis using ground motion earthquake equation predictor. This is the 𝗏𝗃 is a Geological Survey of India's map on which the seismic map of the area is prepared, and this is where the Ayodhya Mandir is located. So the analysis indicated that a geological fault at a distance of approximately 15 kilometers from the site is the critical fault for the Ram Mandir. It is generating a largest peak ground acceleration of 0.22 G for an earthquake magnitude of 6.0 on the Richter scale. So the possibility of liquefaction during earthquakes when the soil tends to behave like a liquid. So this has been done as per IS code, IS 1893/2016. So this IS 1893, it divides the area, the whole India into 5 zones. So Ayodhya actually falls in just at the boundary of zone 3 and zone 4. Most designers consider it in zone 3 because it falls within just inside the zone 3 area. But considering the importance of this structure, the analysis was done treating it in earthquake zone 4. So the design earthquake magnitude was taken as 6.5 on the Richter scale, and the peak ground acceleration was taken as 0.24 G. The design groundwater level was taken as the HFL of the Sarayu River, that is 11 meter depth. So the results of the analysis prove that liquefaction is not likely to occur during the design earthquake. So structural integrity against the maximum considered earthquake. This is equivalent to a seismic event with a 2,500 year return period. So this is what has been considered in the design. Just let's get into the layout. So this is the layout, the 𝗏𝗃, the 𝗏𝗏, the 𝗏𝗏 and the 𝗏𝗃. So all based on the ancient texts like Mansara, Mayamata. They mention the site plan components, design principles, plan form, proportioning systems, building materials to be used, depth of foundation, etc. Many of the ancient temples have also been designed on these principles. I just take the name of a few ones. The Brihadishwara temple in Tanjavur, Tamil Nadu, Jagannath temple in Puri, Odisha, and also the Khajuraho temple all these have been built with the same principles which are given in this configuration here. So this is how it is. The dome here, it weighs about 7870 tons, supported on 15 columns. The 𝗏𝗵𝗿𝗃 here has 48 columns. The temple building has dimensions of 380 feet by 250 feet. 392 pillars on the ground floor. 160. Total 392 pillars. 160 on the ground floor and 132 on the first floor. So you can see the various units here. Let's look at the foundation loads. The Garbhagriha, the foundation depth was around 7.64. Area is 576 square meters. And the total loading intensity is as high as 380 kPa. In the 𝗏𝗵𝗿𝗃, 𝗏𝗵𝗿𝗃 and all, somewhat lower intensity, also very high, 250 to 280. The platform area outside the main temple and the Parakota, which is the boundary wall, the pressures is range of 130 to 150 kPa. The landscape area, of course, lightly loaded, 30 to 50 kPa. So this is the loads on the temple structure for the various facilities. What is the design criteria that's most important? So the main thing was that design life is to be taken as 1,000 years. As you know, most of the modern buildings design life is taken anything between 50 and 100 years. So going to 1,000 years is a huge change. The important requirements to be considered for the foundation design are, firstly, differential settlement the structure cannot tolerate, because we are not using steel and it's a stone masonry structure. So differential settlement has to be close to zero. To minimize the differential settlement, because anything you build, the ground will settle. So to minimize the differential settlement, total settlement is prescribed as 12 mm. So if the total settlement is 12 mm, the differential settlement we were hoping will be much less than 4 to 5 mm. And this much the structure should be able to tolerate. So you ensure safe load transfer of the superstructure loads to the foundation. We are talking about vertical downward, upward, and horizontal loads, particularly during seismic events. Ensure durability of the foundation material for effects of weathering and also impacts of underground water currents. So the foundation shall withstand the wind loads and the seismicity of the area. So this is the design criteria. Now some constraints was put on the designers, mainly the temple architect. As I told you, 𝗏𝗵𝗿𝗃 ji, he had specified that the steel shall not be used for construction. The steel is prone to rusting. It will reduce the life of the structure. The ancient temples do not use steel. The magnetic field around the steel will affect the divinity of the statue. This is what was believed, that the vibration between the god and the devotee may be affected. So once you eliminate the use of steel, civil engineers are constrained that masonry structure cannot withstand tensile stresses. Normally, in the basic concept of structural engineering, the steel is designed to withstand the tensile forces. Secondly, the design life of the temple is too long, as against 50 to 100 years for modern construction. Temple Trust has a vision that it should survive for 1,000 years. So, what were the foundation alternatives considered? Let's have a look at this. Several alternatives were proposed by various experts. So the first one, of course, that you have raft foundation bearing on the soil at shallow depth, but because there is a substantial thickness of fill, and the compaction of the fill, its thickness, all varies from location to location. Total and differential settlements shall be large. You cannot control the relative movement. So this option was not feasible. So this was rejected right at the start. The second was raft foundation supported by piles. So a hybrid pile raft foundation together with the diaphragm wall for confinement. What the diaphragm wall will do is it will help you to restrict the differential settlement. Very reliable and safe foundation system used for various modern tall buildings. It will also ensure that total and differential settlements are within the limits. So, to make this assessment, some test piles were installed and load tested vertical load as well as horizontal loads. While piles itself passed, there were some questions on the integrity of the piles from the pile integrity tests. So it was decided that it's unsatisfactory and risky. Raft foundations, depending on these can be supported on jet grouted columns. So high pressured jet grouting can strengthen the soils effectively and restrict settlement. It's a viable option, particularly for high bearing pressure and stringent settlement restrictions. So by varying the spacing between the jet grouted columns in areas with different loading intensities, total and differential settlement can be controlled. Raft foundation supported on vibro columns. This was another option which was proposed. So that vibro stone columns, it's a very reliable foundation scheme. Stone columns 600 to 800 mm diameter. These could penetrate into the fill, and you can seat it on the dense soils with SPT value of 40 to 50. So this would require about 17 to 19 meters below the ground level. It's suitable for bearing capacity of up to 200 to 250 kPa. But because the Garbhagriha, the loading is 350 to 380 kPa, it is uncertain. Load tests will have to be done to prove it. And so there was a little concern on whether it is suitable or not. The last option which I will propose here is the open excavation to 12-meter depth with engineered backfill. Open excavation, you do it to 12 meters, which is the general thickness of the fill in most areas. In the Garbhagriha, it was carried out to 14 meters. Compact the soils with a vibro roller, then controlled in engineered fill material may be placed with layers with thorough compaction. Do load tests and then construct the raft over it. The stress will be distributed over the compacted fill. So stresses in the soils below will be significantly less, and the supporting soil is dense sand. So the uncertain behavior of the fill is eliminated. So you know that differential settlement will not occur. So just a little more details about these various options. So this is what was the hybrid raft and a pile foundation. The concern is that since you cannot use steel, so the plain board cast in situ piles was casted. Option of using fiber reinforced glass polymer reinforcement instead of steel reinforcement was evaluated, but not considered due to lack of availability and insufficient experience in using such options. Both L&T and Tata Consulting Engineers preferred the use of piles. Finite element analysis using Plaxis 3D software was performed to evaluate this option. The finite element analysis model, this is the one which was analyzed. The estimated total settlement was quite large, about 114 mm. So this option was given up. So vibro stone columns, this is a well-established proven technology. Improvement will be done for the entire temple footprint plus 20 meter beyond the temple perimeter, so that you can ensure peripheral restrainment. In situ full-scale trials plus in situ testing and footing load tests shall be done to establish the design parameters. But the vibro stone columns are not suitable for the Garbhagriha and Gud Mandap, since the loadings in this area is very high. Option of using stone columns for the outside the main temple for the Parakota and other areas was assessed, but after detailed evaluation, this option was also abandoned. Jet grouting, this is the scheme in which you have the rig into which you pump a high velocity jet of cement slurry. This is mixed with the soil, rotated and pulled up gradually so that it forms the columns. So this is how the columns are formed. So the high pressure jet grouting can strengthen the soils effectively, restrict the settlement. It's a viable option for high bearing pressure, stringent settlement criteria for the dome of the Garbhagriha. Can be used for other structures also. The spacing between the jet grout columns, they can be optimized depending on the loading. So this is the scheme. As I told you, you would have to go down to around 19 meter depth or so. Over that you place a 500 to 800 mm thick granular blanket, and then a geogrid shall be placed above that to distribute the load. Benefit, of course, is the versatility, adaptability, speed and effectiveness. Drawback is high cost, complexity, uncertainty and environmental impact. The concern was on the longevity of the cement columns and the kind of quality assurance that will be required during construction. So the expert committee decided not to pursue this option. So we come to the option which was actually adopted. After review of these various options, it was decided to excavate to 12 meter depth, 14 meters in the Garbhagriha area, place roller compacted concrete and construct the foundation over the concrete base. The expert committee decided that unreinforced single raft on the improved ground is preferable. Raft foundation can be engineered to meet the requirements of durability and longevity. The finished ground level of the temple is at a higher elevation than the surrounding ground, so that inundation is unlikely. So the deep excavation can also help unearth the archaeological features which are not known. So the single integrated raft. This was the preferred option. Sequential construction from high load intensity to low load intensity segments help to minimize the differential settlement and optimize the foundation the performance of the foundation and the superstructure. This scheme was justified taking into account the ground conditions, the structural and serviceability requirements of the building, economic factors, both time and cost. And main thing was that it will provide an opportunity to have a look at the actual material below the foundation and take decisions as the work proceeds. It also provides an opportunity for the archaeologists to make a detailed assessment and assess whether an ancient temple, whether it exists or not. Such an opportunity to identify the older structure would have been lost to posterity if any of the other options had been selected. So this is the schematic ground, this is the natural ground, and then you have the foundation. This is improved ground, and then you have the foundation. So the excavation here, first we did a slope stability analysis. This was done using a software. So this was the scheme which was proposed. 3 to 3 meter depth, 1 vertical on 1 horizontal, which was the excavation slope. Then 3 to 6 meter depth, 1 vertical to 1 horizontal, with a 2 meter berm at 3 meter depth. 6 to 9 meters, again 1 vertical on 1 horizontal with a 2 meter berm. 9 to 12 meter, again 1 vertical on 1 horizontal with a 2 meter wide berm at 9 meter depth. Slope stability analysis showed the factor of safety of 1.24. For temporary excavation, 1.2 is normally considered safe. So this excavation scheme is safe for the structure. So, but this requires a huge quantity of excavation and removal of earth. Nearly 2 lakh cubic meters of earth was removed. So the excavation started in January 21, and the target was to complete the excavation as soon as possible and to lay the foundation before monsoon. The time available was limited, so the excavation had to be done fairly quickly to meet the targets. Effective logistics planning was required to coordinate the excavation and removal of the large quantity of soil, stacking and disposal. Everything was at stake. So this is how it looked like after excavation. You can see the excavation activity in progress. Then is the engineered fill, which was used. IIT Madras experts were consulted, and the engineering, they advised that the engineering fill should have soft rock-like characteristics. So the option that was considered were well-graded, compacted, granular fill, well-graded, cementitious, compacted, granular fill, and roller compacted concrete. Roller compacted concrete, or RCC, was the preferred option by the expert committee, since its engineering characteristics can be specified and controlled, and a uniform, consistent quality can be ensured. Roller compacted concrete was designed and proportioned using locally sourced ingredients. 25 mm down stone aggregate was used. Portland cement was partially substituted by fly ash to limit the heat of hydration. This helps in reducing the thermal stresses during construction and limits the potential for formation of cracks. So the mix contains fly ash, coarse sand, stone aggregate, and low water cement ratio. The mix has almost no slump. To ensure a stable system, the SPT value at the base should exceed 40 to 50. So laboratory trials were made to establish the desired range of workability that helps to achieve the optimal density for the compacted concrete. The design values of compressive strength, lift joint bond strength, split tensile strength, elastic modulus, all these were the design values were selected, and tests were done to ensure that these properties are met. The soil at the base of the roller compacted concrete should have an SPT value of more than 40. Field trials were performed, and 4 layers of concrete, each 150 mm thick, were placed and compacted thoroughly. Field density was measured using a nuclear density gauge. Concrete cores were then extracted to test the various engineering properties. To place the roller compacted concrete, material was brought in dump trucks, spread by pavers, and compacted using a vibratory roller. During construction, quality assurance plan was implemented to reconfirm the various properties. These tests included field density tests and testing the concrete cores. So the plinth was then constructed on top of this using 17,000 granite stones that were sourced from Karnataka and Andhra Pradesh. The stones were around 1.5 by 0.75 meter by 0.9 meter in size. Each weighed about 2.5 tons each. Now let's talk about the foundation settlement. Since the sand is encountered below the foundation level, settlement is expected to be immediate. So settlement shall progressively occur as the construction proceeds. Long-term settlement is not likely to occur. More than 80 to 90% settlement would have occurred as the construction proceeds. The structure therefore adjusts to the gradual settlement as the construction proceeds stage-wise. The dome of the Garbhagriha is what is sensitive to settlement. By the time the construction of the dome starts, most of the settlement of the lower part of the building, due to the partially constructed structure, would already have taken place. Further, the total and differential settlement shall only be due to the dome structure, which is expected to be small. Post-construction, we expect the settlement to be negligible. As per the records maintained, after a few months of construction of the temple, the measurements showed only 4 mm settlement. This confirmed what had been believed all along, that the differential settlement is very small, so structure is safe. So they quite satisfied that all the safety and functional requirements have been met. So the structure may be deemed safe with insignificant settlement to occur in the coming years. A little about the structure assembly itself. So I told you earlier that no cement or mortar was used. So basically this is a pin and socket joints where this pin goes and sits into the socket. So this has to be engineered very carefully, and the machining has to be accurate so that you get a proper fit. So you can see these the way it was done here. For the pillar connections, for the slab connections, there is these copper brass pins or brass pins which were used. Similarly, this is for the beam connections. These pins. talk about the timelines. So initial geotechnical investigation work was started in July 2020. Foundation stone was laid in August 2020. Excavation was started January to March 2021. The backfilling with engineered fill was done April to September 2021. The raft foundation with the granite blocks, these were done September to November 2021. Then you had the plinth of granite slabs, November 21 to March 22. Temple superstructure construction started January 22 and completed January 24. The inauguration and consecration of the temple, 22nd January 2024. So a little bit about the archaeological findings and interpretations. Archaeological excavations at Shri Ram Janmabhoomi site has been a focal point of significant complex and legal historical debate. Primarily, it centers around the existence of a Ram temple at this site before the construction of the Babri Masjid in the 16th century, which was demolished in 1992. So legal proceedings had involved various archaeological studies, and interpretations were presented to the courts, including the Allahabad High Court and Supreme Court of India, which clearly demonstrates the existence of the temple at this site, old temple. So the excavation reports, there were multiple reports submitted by Archaeological Survey of India, right from 1950 to 1992, and then 2003 to 2005. It revealed various layers of historical artifacts. ASI reported the presence of an ancient structure, large ancient structure, at the site where Babri Masjid stood. The findings included remnants of pillars, lotus motifs, and carvings consistent with Hindu temple architecture. Dating and stratigraphy was also done. The layering of the soil and artifacts suggested this significant structure predated Babri Masjid, and the architectural elements and all the artifacts, these proved that it was identified to be possibly being a temple. In 1990, the excavations suggested the remnants, but the findings were not conclusive. In 2023, which is most significant to this dispute, there were pillars and foundations, a series of pillar bases, and suggested the existence of a large structure, probably predating the Babri Masjid. And alignment and layout of these pillars indicated a substantial building, which some scholars and historians believe could have been a temple. So the findings from the excavations, when this huge excavation was done to 14-15 meter depth, artifacts and architectural elements, including terracotta sculptures, religious motifs, and archaeological fragments consistent with temple construction. Notably, a large slab with inscription in Devanagari script was also found, furthering the suggestions of a Hindu temple. Post holes in structural evidence, everything proved that there is a possibility of a pre-existing structure. So pillars, temple fragments, lintels, and chhajjas, all these were provided as evidence to the court. Again, carvings and sculptures, motifs and symbols, sculptures, pottery, other artifacts. There were also some coins and inscription fragments. So all these are given in the report of Archaeological Survey of India. So many of the architectural remains and pottery shards dated back to the medieval period, roughly around the 16th century, which corresponds to the time when Babri Masjid was constructed. But there were some pre-medieval remains also. So beneath these layers, there were remnants of an older structure. The structure dates back to several centuries before construction of the Babri Masjid. The dating of this structure was generally estimated to be from 12th century to earlier than that, possibly as far back as the 8th or 9th century. There was also mention of a Ram Vishnu temple. The exact age of the old structure was challenging, and it was not easy to pinpoint the nature because of the archaeological evidence, but was considered significant for understanding the historical context of the site. So there were artifacts dating back to the 8th century. So there were evidence of a Hindu temple. There was complex layering. Overall, the artifacts and dating provided crucial insights to the historical layers of the site, but it did not offer conclusive evidence to the specific nature of the structure or its religious significance. The findings contributed to a broader understanding of the site's history, but ultimate legal and cultural decision was based on a combination of historical evidence, religious significance, and legal considerations. So all these were actually correlated with the archaeological findings were correlated with the scientific investigation by NGRI and CBRI. This is what proved crucial. This helped to because the archaeological findings they complemented the scientific studies. The GPR survey indicated several anomalies in the subsurface layers. So these suggested the presence of a large ancient structure beneath the site. Some of this data indicated possible walls, pillars, or other architectural elements consistent with the presence of a significant ancient structure. The electrical resistivity survey also corresponded to presence of large man-made structures. And the findings of the GPR and the resistivity, they indicated the presence of extensive architectural remains beneath the site. So there was a lot of consistency in the findings. The structural evidence corroborated with the findings of ASI. Both the sets of investigations indicated the presence of this large ancient structure. The dating of these layers also were consistent. The architectural features, the structural remains, both scientific and archaeological, suggested these various architectural elements for a large structure. So these correlations reinforced the hypothesis that the site was home to a large temple-like structure before the construction of the Babri Masjid. The findings from the resistivity profiles, everything, GPR, everything was consistent. So the design elements also supported this, and the line with the carvings and archaeological fragments were identified. So all the scientific investigations provided this additional layer. Archaeological artifacts unearthed goes back to the Mauryan, Shunga, and Kushana period of the 3rd century BC. But some radiocarbon dating trace their origins to 1680 BC, almost 3,600 years ago. So these are some of the artifacts which were found, ancient pillars and idols, some more pillars, motifs, and you can see the lotus carvings and all that. Also some idols, terracotta. So this is the temple construction under the temple under construction. Again, the temple almost constructed here. And this, of course, is the temple as constructed and inaugurated January 22nd, 2024. I would now like to conclude Shri Ram Janmabhoomi Temple at Ayodhya, the modern engineering marvel designed to withstand earthquakes as well as intense flooding. The foundation construction of the temple was done by Larsen and Toubro with design consultancy by Tata Consulting Engineers. The final selected scheme developed with innovative construction techniques after meticulous planning included excavation to 12-meter depth, engineering fill with roller compacted concrete. It was placed in 56 layers. The benefit of the scheme, of course, was that it provided an opportunity to investigate the archaeological aspects and unearth the evidence of presence of the old structure, which would otherwise have been lost to posterity. Thank you very much for your kind attention. I will be happy to take any more questions. Thank you.
Thank you so much, sir, for the insightful presentation. Your experience and expertise truly shine through in every aspect of the work you shared today. Now, let's move on to the QA session. I request everyone to please continue posting your question in the comment section and we'll address them one by one. So, first question, like someone had asked, whether you have published any paper on this work.
Karthikeyan, we have submitted a paper to the Indian Geotechnical Journal. It is under review, and after peer review, it will be published probably within a few months. So you may look forward to that. We will post that on our Cengrs website and also on our LinkedIn page. As soon as the paper is approved and published in the journal, you'll have it.
Thank you, sir. Next question is from Anita. Why was it important to test soil up to 70 meters for this project? Does it differ for smaller structures?
Now here it was tested to 120 meters depth. The basic concept is that whatever is your foundation width, you should test to at least 1.5 times the depth, so that you can see the nature of the soil below and what are the layers which are likely to influence your foundation, because the stresses go down quite deep, and if there are any loose layers down below, it could influence the settlement of the foundation. So whatever is your foundation width, you should go down to 1.5 to 2 times. Normally, the thumb rule says that if it's a small foundation, about less than say 8 to 10 meter width of foundation, you would go investigate twice the foundation width below the foundation level. And if it is larger, huge rafts, you would go down to at least 1.5 meters. Thank you. Thank you, Dr. Madhusudan Reddy.
Next question is from Ankit. How do tests like electrical resistivity work? What do they tell us about the soil?
Ankit, electrical resistivity measures the resistivity of the ground. Basically, it would tell you the type of soil, because different kinds of materials will have different resistivities. So a sand would have some resistivity. A clay would have much lower resistivity because you would have clays are electrically charged particles. Similarly, different kinds of rocks have different characteristic resistivities. Also, if it's a dense sand, the current will pass easily. It would have lower resistivities. So, if there are air pockets, if there is groundwater, everything affects the resistivity values. So, that there are published correlations, and there are standard methods by which you can do the and determine the layering from the resistivity data. So the resistivity tells us a lot about how compact the soil is. In this case, resistivity told us that about the anomalies, which means like if there is a void part of a temple structure, so the air is a poor conductor of electricity, so there would be a spike. So or if it is just filled with water, it would in fact be much very low resistivity. If the salinity is high, again the resistivities will be low. So you can make a lot of interpretations from the resistivity testing. But geophysical tests always, you have to confirm it with physical presence, because there could be multiple interpretations which has to be justified. Thank you, Ankit.
There's one message from Vijay Krishnan. Watched your very highly technical presentation for a short while. We, your schoolmates, are proud of your accomplishments.
Thank you, Vijay. Great night connecting to you after such a long time.
Next question is from Ankit. Next question is from Seema. How do you check if the ground improvement measures you actually worked?
Ground improvement methods, you have to verify their success. So, like if you were doing vibro stone columns, so we have done the investigation before this stone column, and you would also do a investigation after the stone column to see how the soil properties have improved. And also we do load tests. In this case, what was proposed was footing load test. So a 2 to 3 meter wide foundation would be cast and load tested. So we know how much bearing capacity you actually will get. Similarly, for jet grouted columns, load tests are recommended. Of course, there are also various other quality assurance measures which are done to make sure that your material is correct and densities are correct. So all those things are done.
Thank you, sir. There's one. Next question is from Ranjit. Foundation without reinforcement, which factor should consider?
Ranjit, what kind of factors are you looking at? The standard structural engineering parameters are what are considered. The stresses, the displacements is what controls everything. You have to make sure that your stresses are within the limits, your displacements are within the limits, and other things like what we had tested because this was a masonry structure, so there was the lift bond stress. If I may.
Yeah. Next question is from Gaurav.
Just 1 minute. So the roller compacted concrete, these are the parameters which were checked. the compressive strength, the bond strength, the lip joint bond strength, split tensile strength, elastic modulus. So all these parameters would have to be checked. I hope it satisfies your question, Ranjit. Yeah.
Yes, sir. Next question is from Gaurav. Why was it necessary to test the ground for the boundary walls and smaller temples too?
This boundary wall was also a very heavy structure with quite a lot of loading. It was quite a wide facility. A pradakshina was planned here, is planned here, so that people can walk across around the temple. So this is not an ordinary boundary wall that you see for most buildings. Also, these small temples, they also had quite a bit of load. These are transferring a lot of load below the ground, and then all the again no steel, so it makes you have to be thorough.
Next question is from Anjana. What were the biggest takeaways from working on such a massive and unique project?
Well, there are always big takeaways from every project that we have worked on. The one thing is that contributing to the project like an expert was something very special, but it was a very humble learning experience for all of us. And and then when we started the work in June 2020, COVID was at its peak, but we were working all the time and testing the samples in our lab. Things were moving on, so it also tested the limits to which we can go, and interacting with the various experts, how to design the structure, what are the requirements, the temple architect's requirements, which were like somebody who was, his family has been involved in the temple construction since more than 2000 years, starting with the Somnath temple. So Sompuraji was a great inspiration. We had an opportunity to work with him on another temple at Mangad also. So these were all, as an engineer, as a professional, I think we have grown one little bit more. Thank you.
Thank you, sir. Next question is from Priya. Are there things you would do differently if you worked on a similar project again?
Well, this is a once in a lifetime opportunity as far as I think I am concerned. Never done anything like this before. And what actually made this so complex was the history, the court cases, and the archaeology. So if there was no history, if there was no archaeology, maybe we could have done a lot more. Of course, again, if it's not a temple, a regular building that we see all around, there's lots of other things which could have been done, and probably much more efficiently at a lower cost. But history and archaeology are something which are different from project to project, in case there is anything like that. So we don't encounter archaeology in most of our building projects. So I really don't know, Priya. Maybe if something like this comes again, we'll have to do fresh thinking on what can be done. Thank you.
Next question is from Sangeeta. Which advanced tools or techniques were most useful for this project, and how can a beginner learn to use them?
Sangeeta, there were, if you are a geotechnical engineer, you would be aware that routine boreholes are the conventional method for investigation. Now, this was supplemented by cone penetration tests and pressure meter tests. These are the advanced technologies which are currently available in India, and they have been very useful in making a better assessment of the soil bearing capacity and the settlement. There are various other tests, geophysical tests, which I had shown you. The MASW, the electrical resistivity tomography, the ground penetrating radar. These are all geophysical tests which can give you some fantastic data right at the beginning before you start the investigation. So if you have the geophysical data, you know what to look for and where to look for it. And yes, there are, at the master's level in many of the engineering colleges, they do teach you, but practical experience is all about doing it yourself. So you could look at joining companies which do these different kinds of tests, and you would be getting an opportunity to learn and become an expert. Thank you, Sangeeta.
Thank you, Mr. Khan. Next question is from Ibrahim Khalil. What are the other foundation options, pikes, etc., explored, and why raft foundation was selected eventually?
Ibrahim, my presentation had concentrated on this. The various options that were considered were the piled raft foundation, the jet grouting, the vibro stone columns, and all that. And I had also explained that raft foundation was selected because there were various benefits which were seen in the option for raft, because it is number one, it will allow you to have an opportunity to look at actually what was down below, and make an archaeological assessment, and then you can do a careful integration of the various units so that the differential settlement can be controlled effectively. This whole presentation was about that. So I'd suggest that you have a look at the YouTube video again, and maybe you could just mail me if you have any questions, and then we can move on from there. Thank you.
Thank you, sir. Today's last question is from Sushil. How do you determine the soil properties for such a deep foundation? What are the key factors you consider?
Well, the most important soil properties which you have to determine are the shear strength parameters, the density, the modulus of elasticity, the your over consolidation ratio if it's a clay, and such parameters. So the borehole testing, the laboratory testing, the in situ tests like pressure meter and cone penetration, all these tests were used to consider this. And the design profile which I had presented, that summarizes the various parameters that were determined and which were used for the foundation analysis. Thank you.
Thank you, sir. Thank you, sir, for addressing these questions with such clarity and depth. And to all our attendees, thank you so much for your active participation and thought-provoking questions. Before we wrap up, I'm excited to announce our next webinar scheduled for 15th March 2025. In the upcoming session, we'll delve into the inaccurate or unreliable geotechnical reports. So stay tuned for more details, and as always, feel free to reach out us with your questions or connect us through our social media or via mail. Once again, thank you, sir, and thank you all the attendees, and we really look forward to seeing you at our future webinars. Have a wonderful day. Thank you, sir.
Thank you, everybody.